Dear students, in this session, we are now going to study about the properties of the furan. So first let us see the furan properties, physical properties and then chemical properties. Dear students, please watch the video till the end, then only you will get the complete idea about the properties of the furan. Especially here we are important topic is the electrophilic substitution of furan. So which may ask in your exam for 4 or 5 marks. So first physical properties of furan, if you see, so it is also like pyrrole, colorless liquid. It is also colorless liquid which is insoluble. It is completely insoluble in water and readily soluble in organic solvents. Soluble in organic solvents. Okay, if you see its odor, it is also having the chloroform like odor. The odor is like chloroform, and if you see its boiling point, which is one of the very volatile, which has a very less boiling point, that is around 31.4 degrees centigrade. 31.4 degrees centigrade. So in the case of pyrrole, we had a greater boiling point because it shows some hydrogen bonding extent. Here that is not possible, hence it is having a very less boiling point. So these are the physical properties of the furan. Now we'll discuss the chemical properties of furan. Like pyrrole, furan also shows a lot of reactions, but the most important reaction in this syllabus is the electrophilic substitution reaction. So it also undergoes easily the electrophilic substitution reactions, and it is very much similar to the electrophilic substitution of pyrrole. In the same way, thiophene also undergoes the electrophilic substitution reactions. Hence, we are not going to discuss the reactions of thiophene because it shows almost all similar properties. If they ask about thiophene also in your exam, you can easily write. So now we'll discuss the electrophilic substitution reaction in furan. So if you see the furan, okay, here also we have 4 hydrogens for the electrophilic substitution reactions. So this is position, oxygen is position 1, so 2, 3, 4, 5. Here also 2 and 5 are equivalent, and also 3 and 4 are, these both are equivalent. So hence if the reaction takes place at second, which is nothing, which is similar to the fifth. If the reaction takes place at second, third, which is similar, which is same as fourth. That's why here also we get the 2 positions, either 2 or third. Second or third positions will be prior. Let us see which position gives the most stable compound. Now we'll see the electrophilic attack at second position. Electrophilic attack at second position. Okay. Pyrrole, the electrophile when it is introduced, it attacks to the pyrrole ring. Sorry, furan. Sorry, it is furan. Furan. So when it is attacked the second position, the electrophile, there is an hydrogen before it, and here also an hydrogen. Here we get the positive charge at the third position, as it is same. So it is forming a carbocation intermediate, which is an unstable, which also shows resonance like a pyrrole. So these electrons shift here. So now this bond become double bond. Here we got the positive charge, the electrophile hydrogen, Here we got the positive charge. Yeah. Yes. Now these electron will shift here and this become a double bond. This become double bond, electrophile and hydrogen. The oxygen gets the positive charge because around the oxygen there will be third bond now, three bonds. So oxygen become the positive charge. So finally this hydrogen will be eliminated and giving us the product. So with the removal of this hydrogen, we will have the product, electrophile, that is 2 substituted furan. 2 substituted furan. So this much we can find in when the electron attacks at the electrophile attack at the second position. The same thing we'll see for third position when electrophilic attack takes place at third position. At third position. Okay, so I've taken furan. So when electrophile is introduced, which is attack the furan ring. So now the electrophile has been introduced at the third position. So there is usually hydrogen. So the second position gets the positive charge. The second position gets the positive charge. So here also carbocation formed, which can be showing resonance. So the lone pair of electrons in the oxygen on the oxygen will give electron, and here it becomes double bond. So here also for oxygen we got the 3 bonds around it, hence it shows the positive charge over the oxygen. So there is no more resonance structures because it cannot give electron, it becomes 4 bonds, which is impossible in the case of oxygens. So these two are the resonance structures for the carbocation formed in the furan. So here also with the elimination of that proton, we get the third substituted or 3 substituted furans products. 3 substituted furan. Okay, here when the electrophile attack at the second position, we got the 3 resonance structures. And when the electrophile attacks at the third position, we get the 2 resonance structures. Now you can yourself tell me that which position is most easily prior for the attack in the case of furan. So here you can see, as you all know, more the number of resonance structures, more is the stability. So here we got the 3 resonance structures, hence the electrophile attack at the second position is most prior. It gets the highest priority, and here you only get the 2 resonance structures, which is less, it is giving a less stable compound, hence the second position, at second position the electrophile attack is more easily takes place. So here the second position is most prior than the third position because it gives the more number of resonance structures. Here also the same thing. Here this resonance structure gets the oxygen with positive charge. Here also oxygen with positive charge. Both are unstable. Both are unstable. But at least here these 2 resonance structures are stable. the first and second one. Here this one is stable. Okay, here at least we get the two stable resonance structures. So more stability we can find in this case. That's why the second position, the carbocation forms three resonance structures, at least two of which are more stable one are stable ones. Here the only one is stable and this is unstable of the two resonance structures. Hence the second position, the electrophile attack takes place easily in the case of furan like pyrrole. So this is usually asked for 4 marks, either for the pyrrole or furan, or pyridine will ask in your exam. One of which will definitely ask in your exam. Please note it down. Okay students, now we'll see examples of electrophile substitution reactions. So we'll see the nitration. Here the nitronium ion will replace the proton in the furan. So furan, when it undergoes nitration using HNO3 in presence of acetic anhydride, as usual in the case taken place for the pyrrole, acetic anhydride. Here the furan also easily undergoing electrophilic substitution reaction. That's why I do not need any higher catalyst like sulfuric acid or like. So furan, when it undergoes electrophilic substitution, the nitration using nitric acid in presence of acetic anhydride, as second position is the most prior position. So that is why at the second position only the nitration takes place. So it gives us 2 nitrofuran, 2 nitrofuran. So this byproduct is the, as usual, acetic acid, CH3COOH. Acetic acid is the byproduct. So this is when furan undergoes nitration using nitric acid in presence of acetic anhydride, we get the 2 nitrofuran. Now we'll see the second example, that is chlorination. Chlorination, like pyrrole, it also easily and readily undergoes chlorination, but not much like pyrrole. More than benzene, lesser than pyrrole. So when furan undergoes chlorination, okay, this is also at cold condition only. Okay, so here the chlorination will give the mixture of two compounds. The second position, as usual, is most priored. So that is 2 chlorofuran. Along with it will give, second and fifth both are equivalent. So that's why it also give a dichlorofuran. That is at fifth position, and also second position we get the chlorination, that is 2,5 dichlorofuran. So when furan undergoes the chlorination, which takes place readily, hence we get the mixture of 2 chlorofuran and also 2,5 dichlorofuran. So this is about the electrophilic substitution reactions in furan. So if you know the pyrrole, it will be easier to you to get this electrophilic substitution reaction in case of furan. So please, thank you. Please watch my video and like it. Share with your friends. Please share with your friends, and please subscribe to my channel. Thank you. Hi students, today in this session we are going to discuss about the properties of pyridine. So already in the last two classes we have discussed about the physical and chemical properties of pyrrole and thiophene. So in this session we are going to discuss the physical and chemical properties of pyridine. So in the first physical properties, pyridine is a colorless liquid, a colorless liquid. And actually in our lab, if we see, it is available in a small light pale color, in a light pale color, because sometimes it may undergo some kind of oxidation. So that's why it is available in a light pale, or it is actually a colorless liquid. And if you come to its smell or odor, it has a fishy odor. It has a fishy odor. So the fish smell. And it is also miscible in water. So it is one of the rare quality. It is miscible in water, and it is one of the very good organic solvent that you already know, and it is very important. Miscible solvent. It is one of the very important miscible in water. Miscible solvent in water. Yeah, miscible in water or miscible solvent in water, and it is one of the very important industrial solvent, very important industrial solvent in organic chemistry. And if you see its boiling point, the boiling point is about 115 degrees centigrade, around 112 to 116 degrees centigrade, which is the boiling point of the pyridine. Pyridine can be stable, okay, it is not much volatile. So this is about the some physical properties of pyridine. Now we'll see the chemical properties of pyridine, means that is the reactions of pyridine. In chemical properties of pyridine, we may see so many number of reactions, but this electrophilic substitution reaction is one of the property for a criteria of the aromaticity we'll see in the pyridine. As you all know, as we already discussed when we discussed about the aromaticity of pyridine, the pyridine is not easily undergoing or readily undergoing the electrophilic substitution reactions, but still at vigorous conditions at contrast temperature, high pressure, at that situation even pyridine also undergo some electrophilic substitution reactions. So before the electrophilic substitution reactions, let us see which position of the pyridine is more preferred for the electrophilic substitution where the electrophile can be attacked. So if you see the structure of pyridine, it is almost similar to the structure of benzene, where just there is a replacement of a nitrogen with the carbon. So that's why even if you see its physical properties also, it shows many of the reactions similar to the benzene. So most of the properties are similar to the benzene. So even chemical reactions also similar to benzene. So here in the nitrogen, the position 1, 2, 3, 4, 5, 6. All these carbons have hydrogen, so these hydrogen can be replaced with an electrophile. So such type of reactions are electrophilic substitution reactions. So in this case, you see there is second and sixth carbons are equivalent. They have same properties. Second and sixth. The same way, third and fifth are also having same. They are equivalent. The fourth is the different fourth one. So there are three positions we may see where the electrophile can easily be attacked. So second or sixth, third or fifth, or the fourth one. So these three positions. Let us see which position of the pyridine, which position in the pyridine is more preferred for the attack of the electrophile. So let us see now the electrophilic attack at second or fifth or sixth position, third or fifth position, or at the fourth position. We'll see now electrophilic attack at second R of sixth position. So this is pyridine. Okay. Now when an electrophile is introduced, it is going to attack at the second position now. So we'll get a carbocation. The electrophile has been introduced at the second or sixth position. So here at the third position we get the carbocation. The remaining is same. So this carbocation can be, it is an unstable intermediate which can be stabilized by resonance. If you see its resonance structure, these pair of pi electrons will be shifted here. So there is a creation of a double bond, and this positive charge will shift from this position to the fifth position. The electrophile, hydrogen. Here also hydrogen, there is one hydrogen. Each carbon has one hydrogen. So here the positive charge is shifted. It became a double bond. Here also double bond. So now this double bond will shift here. So there is a formation of a double bond, and the positive charge will shift to the nitrogen atom. See, this is happening. Electrophile, hydrogen. Yeah, there is a formation of a double bond here, and the positive charge come over the nitrogen. So in the last, this hydrogen will be giving its electron and forming a double bond, and it will be eliminated. So these three are the resonance structures. With the elimination of the proton, it is going to form a electrophile substituted pyridine. The electrophile is at the second position. So this is 2 substituted pyridine. So at second position we have an electrophile, 2 substituted pyridine. Okay. Here we are forming 3 resonance structures. These 3 are the resonance structure formed when an electrophile attack at the second position of the pyridine. Okay. So let us see now the electrophilic attack at the third position. Electrophilic attack at third position. Third and fifth are equivalent, so I can write third or fifth position. Both are same. Yeah. So this is pyridine. Okay. Here now when an electrophile is introduced, so it is going to attack at the third position. So let us see the carbocation intermediate formed when electrophile attacks. So electrophile shifted here, attacked here, and there is hydrogen. The positive charge come at the second position with the hydrogen. The remaining is same. So this carbocation also can be stabilized by resonance. Let us see its resonance structure. These pair of electrons will shift here in formation of a, not here, yes, here. These pairs will shift here. So here there is a formation of a double bond, and the positive charge will come over on the nitrogen atom. Let us see that. No, not positive charge. Sorry, positive charge come over at this carbon. So these electrons will be shifting here, and the positive charge will shift here to this carbon, the carbon number 6th. Is the formation of a new double bond, and the positive charge come over at this position. Here, not here. The electrophile and hydrogen. Now this can also be stabilized by resonance. These electron will shift here, and this forming a double bond here, and there is a formation of a the creation of this positive charge at the carbon number 4. Yes. Finally, this hydrogen will give its electron, forming a double bond, and it is eliminating. So here the proton elimination we'll see. When proton eliminated, it is going to form a 3 substituted third position. There is a electrophile. There is an electrophile has been substituted. So this one is the substitution at a second one, 3 substituted pyridine. Here also we found 3 resonance structures. Here also we found 3 resonance structures. As you already know, the when a carbocation gives more number of resonance structure, that will be a stable one, and that will be the preferred one for the electrophilic attack. When in second position and the third position, we get the same number of resonance structures. Now we'll see the electrophilic attack at fourth position. So this is pyridine. When an electrophile has been introduced, so this pi electron will take that electrophile, and now the electrophile, this is a proton, and the positive charge will be forming at this position. Double bond, double bond. Okay, this carbocation can be stabilized by resonance, so this will give electron. As it is an intermediate, I am putting it in a square bracket. It is unstable one. So now here it has become a double bond, and the positive charge will shift to the nitrogen atom. This hydrogen electrophile is become double bond, and the positive charge over the nitrogen. And this is also show another structure, resonance. This electron will shift now and become double bond, and the positive charge shift from this nitrogen to carbon number 2 or third position. Yeah, the positive charge, it became double bond is earlier as it is. Yes, this is the third resonance structure. No more resonance structure here. Now this hydrogen will give electron, and with the elimination of this proton, it is going to form 4 substituted pyridine. So this is the product. Sorry, I'm not much comfortable at below portion to write. That's why these structures are not exactly the same. Yeah, no, electrophile. This is 4 substituted pyridine. Yeah. Yes, here also we got again 3 resonance structures. 3 resonance structures. Here also 3. In case of pyridine, an electrophile attack at second, third or fourth position, we got the same number of resonance structures. It was easier to find out which is the most preferred position in case of furan and pyrrole, because there we used to get 3 and 2 structures. The which one gives the more resonance structure, which will be that would be the most stable structure, and that would be giving the electrophile. So at that position, electrophile used to attack with stability. But here if you see all the positions, whether second position, third position or fourth position, all of them are giving 3 resonance structures. So now we have to see the stability of these resonance structures. So when electrophile attack at the second position or sixth position, so here carbocation, here also carbocation, but the third one, this structure has the nitrogen with the positive charge. As you all know, nitrogen is an electronegative element which cannot hold positive charge. So that's why this resonance structure will become unstable. Unstable. So the stability, resonance stability will be only by these two structures. So in the case of electrophile when attacks at third position or fifth position, if you see here, there is a carbocation, here also carbocation, and here also carbocation. All three are stabilized here by resonance. And okay, and when the electrophile attack at the fourth position, see here there is a carbocation, here there is a nitrogen with positive charge. So again the same. So when nitrogen has a positive charge, so it is an electronegative element, hence this structure also become unstable. Okay, and this one is again carbocation, it could be stabilized by this resonance. So now we can say which position is most preferred. Yes, the third or fifth position is the most preferred position for the electrophilic attack in the case of pyridine, because all three structures give carbocation which can be resonance stabilized, and here we got the three structures. Here we only get two stable structures, here also we got only two stable structure. Hence the electrophilic substitution, if attacks if it takes place in the case of pyridine, that will be only at the third position. Okay, because the pyridine is not readily undergoing the electrophilic substitution. So here the third position is the most priority, it gets the highest priority, or it is only the position where we can find the electrophilic attack, because these two will give an one unstable structures. So the third position is the preferred structure, preferred attack, preferred position for the electrophilic attack. Now we will see the examples of electrophilic substitution reactions. So as pyridine is not easily undergoing electrophilic substitution reactions, we cannot see all the kind of electrophilic substitution reactions. Very few reactions can be possible. We will see nitration and halogenation, two reactions. And these are very important for 4 marks in your exam. Please note them down, because this much if you write, you will get definitely the all 4 marks. Now we'll see the examples, nitration and halogenation. Now we'll see nitration. Here the nitronium electrophile, that is NO2 plus, will replace the proton. So here the pyridine undergoes nitration when it is treated with KNO3, potassium nitrate salt. Here we do not require HNO3, because HNO3 is not much concentrated like salt. So that's why we are getting a concentrated salt like potassium nitrate, and it is treated with sulfuric acid, which also catalyze the reaction. Okay, the mixture of potassium nitrate and sulfuric acid has been used, and this is heated to 300 degrees centigrade. As we already know, pyridine not readily undergoing this electrophilic substitution reactions, so we need to heat this reaction to 300 degrees centigrade. Then only there is the electrophilic substitution takes place at third position. Yes, that is nitrate, NO2, 3 nitro pyridine. As you already earlier seen in case of furan and pyrrole, the reaction used to take place in a cold condition, because they both are readily undergoing electrophilic substitution reaction. Here we need to heat. That's why at vigorous condition only the pyridine undergoes electrophilic substitution reaction. So pyridine undergoes nitration by using potassium nitrate in concentrated sulfuric acid when it is heated at 300 degrees centigrade to give 3 nitropyridine. Yes. So now we'll see another example, that is halogenation. The one thing you need to notice that the pyridine does not undergo chlorination. No chlorination here, because I have already seen chlorination in the case of furan and pyrrole, especially in the case of pyrrole, all positions used to get the chlorine radical, sorry, chlorine electrophile, that is chloronium electrophile. But here this chlorination is not possible, as it is not easily undergoing the reaction. But we can do bromination, because bromination is also an example of halogenation. In case of bromination, pyridine may undergo bromination. Okay, pyridine undergo bromination. Okay, so when pyridine is reacted with bromine, here this reaction is very slow, so it will take around 2 days to complete the reaction. 2 days, about 48 to 50 hours it needs for the reaction to complete. It's a very slow reaction. There, in the case of pyrrole and uh, furan, we could do it in a minutes, but here it will take around more than 2 days, 48 to 50 hours. But the reaction takes place and we get the 3 substituted bromine derivative of pyridine, that is 3 bromopyridine. 3 bromopyridine, pyridine to 3 bromopyridine. So pyridine undergoes bromination with bromine, and that reaction takes place for about 48 to 50 hours. Then we'll get 3 bromopyridine. But though reaction takes place, this yield of the reaction is very much poor. Whether in case of nitration or in bromination, the yield will be very poor. Poor yield, around maximum around 30 to 40% we can get the product. Here also poor yield, there also poor yield is very much poor, because it is not suitable. The pyridine is not easily, or it is not suitably undergoing this electrophilic substitution. These reactions are not suitable for the pyridine. So we know the reasons, right? The one is this nitrogen is a electronegative element which pulls all the electron towards it and making the benzene ring with a partial positive charge. So that is what benzene ring itself is electrophilic. So there is no reaction. How the reaction takes place between electrophile. So that's why. So one thing, electrophile cannot attack the benzene ring when pyridine is there, when nitrogen is there. And another reason, this lone pair are free electrons on the nitrogen, so those will attack this, those will be attacked by the electrophile, hence it is going to form pyridinium ion. Instead of the substitution reaction, there is an addition reaction, okay, at the nitrogen may takes place. So this is about the examples of electrophilic substitution reactions, nitration and bromination we can see. Thank you for watching. Please like my videos, please watch completely, then only you will get the complete idea about the topics, and please subscribe my channel. Thank you. Hi students, today in this session we are going to study the last topic of this chapter, and that is a comparison of basic strengths of pyrrole, pyridine and piperidine. This is also, as you know, this is one of the very important question that is asked in your exam. Okay, so if they ask all 3 comparatives, all comparison of basic strength of all these 3 compounds together, then they will ask for 4 marks. Either they will ask the questions like the basic strength of pyrrole and pyridine, or the compare basic strength of pyridine and piperidine, then it may also ask for 2 marks. So it is one of the very many times it has been asked in exams. So one of the very important topic. That's why we'll see it. Okay. So first we should know about acidic. What is basic nature? The one basic nature according to Bronsted-Lowry's theories, the one has to accept the proton. It has to undergo protonation. So in that on the base of that theory also we'll discuss the basic strength. And also another theory here, you can all see there they have a lone pair of electrons and over in nitrogen atom, hence we can also give the basic strength on the basis of Levy's theory. So the pair of electrons donators, the donors, electron pair donors are Levy bases, and those which accept the protons are Bronsted bases. Both theories will apply, and we'll see the basic strength of these 3 compounds, which is more basic, which is less basic. Yes. Now first I will discuss how they will react with the protons when they undergo protonation. First discuss the what is Bronsted theory. I'll discuss there. Yeah. First compound, if you take pyrrole is a 5-membered heterocyclic aromatic compound. Yes. So in the case of pyrrole, when we add an acid like HCl, okay, if it is able to accept this proton, it is going to form N double bond plus H and HCl. Yes, okay. Base and acid, when the base and acid react, they form salt. So when pyrrole undergo protonation, so it is going to form pyrrole HCl, right? Hydrochloride. Pyrrole hydrochloride. Yes, the one thing you should know here, so here these electrons are involving in aromatic. So they are forming the aromatic sextet. They are delocalizing electrons inside the ring. But if you see here, those electrons have gone because the proton has been accepted by the nitrogen. Hence here there are 6 pi electrons, here only 4 pi electrons. Hence it lost aromaticity. There is a loss of aromaticity. It lose aromaticity. As you know, aromatic compounds are more stable compound. So if it is able to lose this aromaticity, this compound will become unstable. This compound will become unstable. If it is giving an unstable salt, that reaction does not possible and does not undergo. So then hence this pyrrole cannot undergo protonation. So it cannot accept that proton, because if it accepts this proton, it will lose its aromaticity. Hence it is not a so good Bronsted base. If you talk about electrons, so these lone pair of electrons are not available because they are involving in the delocalization. So it is not able to donate that pair of electrons. It is also not a good Levy space. It is not a base especially. So it is one of the very weak base. Hence it becomes very weak base. Okay. Now the same thing will apply for the pyridine. So when we take pyridine is a hexo pyridine. So that is 5-membered. It is a 6-membered heterocyclic ring. So in case pyridine when it is reacted with the acid like hydrochloride as hydrochloric acid. So this also accept that proton. Yeah, that H has been come here, and it is compensated with the positive charge is compensated with negative charge. So it is going to give pyridinium hydrochloride. Pyridinium hydrochloride, which is one of the stable, because here we do not lose any aromaticity. The aromaticity is retained. There is no disturbance, no disturbance in disturbance, no disturbance in aromaticity. So it still retain that aromaticity. Hence, this is stable one. This is a stable one compared to pyrrole. So pyrrole gives an unstable salt, but pyridine can give stable salt. So stable salt. Okay, sorry. So here if you see, it can easily accept that proton, hence it is a good Bronsted base. And these lone pair of electron do not involve in the aromaticity, or it is not, they are not delocalizing. They are very much free in the sp2 hybrid orbitals, so they are available, easily available for this proton. So hence this nitrogen or this pyridine whole compound can donate this lone pair of electrons. Hence it is also one of the good Lewis base. Okay, this is a good or base. It is a good base, stronger one compared to this which one, pyrrole and pyridine. So hence pyridine is the stronger base compared to pyrrole. So now I can put a symbol. Pyridine is weaker in basic strength compared to the pyridine. Sorry, pyrrole is less basic compared to pyridine. So now we'll see another compound, that is piperidine or piperidine. See here. So this piperidine or piperidine is also a 6-membered heterocyclic ring, but it is aliphatic in nature. It is aliphatic. It is not aromatic. So it is aliphatic one, piperidine. Yeah. So when it is treated with an acid like HCl, it easily undergo that protonation like a secondary amine. It is actually a secondary amine. Yeah. Piperidine, here Cl minus. So it is going to give piperidine hydrochloride. Piperidine hydrochloride. Yeah. So here also same protonation is possible. Here also protonation is possible. So hence these are good bases. Okay. The good Bronsted bases which accept easily the proton. Yes, of course. But the one thing here, it is a lesser Lewis base compared to here in the case of piperidine, because the one thing, these lone pairs, though they are not involving in aromaticity, but they are involved by that is influenced by that aromaticity. So that's why. And also one more thing, this nitrogen is sp2 hybridized, of course, but here it is sp3 hybridized, sp3 hybridized, so like secondary amine. So you please remember, the nitrogen in sp2 hybridized, nitrogen in sp2 hybridized is more electronegative, is more electronegative than the nitrogen in sp3 hybridized. You please remember this one. The nitrogen in sp2 hybridized is more electronegative than the nitrogen in sp3 hybridized. Yes, here you see here, this is sp2 hybridized, this is sp3 hybridized. So these electrons are in sp2 hybrid orbitals, these are in sp3 hybrid orbitals. So as it is more electronegative, what is electronegativity? Electronegativity is the acceptance or attracting the electrons, not giving electrons, not giving electrons. So hence the rate of donation of these electrons or rate of providing these electrons or the availability of these electrons, the rate of availability of these pair of electrons is less compared to the rate of availability of the electrons in the piperidine. You got this? These electrons are available, these are also available, but these are very much available and easily can give it to the other orbitals, but these electrons are not possible. Hence, this is a weaker Lewis space, it is a stronger Lewis space. It is a weaker base, it is a stronger base. So this piperidine become a very stronger base, strong base. Now, can I put the simple? So, pyrrole is less basic than pyridine and pyridine is less basic than piperidine. Please remember this one. Okay? Yeah. And it is also yes, it is also confirmed by their pKb values. You know, the one which has a more pKb value, that is more basic. So if you consider the pKb value of, I'll write here, the pKb value of pyrrole is just around 3.4. And if you consider the pKb value of pyridine, this is about 5.2. This is about 5.2. And if you see the pKb value of piperidine, it is about 11.2. See the value? This is the more stronger base. So that also you should remember, more the value of pKb, that means more is basic, more or high basic. Okay, so the pKb value of pyrrole is 3.4, pKb value of pyridine is 5.2, the pKb value of piperidine is about 11.2. So that is having a higher value, hence it is the more, and compared to here it is the most basic, it is more basic, it is less basic. Okay, so now in this method we can express the basic strength and we can compare the basic strength in three manners. One is about according to Bronsted theory, means when they accept the proton. So here when it pyrrole accept the proton, it gives pyrrole hydrochloride, which is unstable because it loses its aromaticity. These electrons should be involved in the delocalization. When they accept the proton, those electrons will come out of the aromatic ring. So hence this is not possible. Hence the pyrrole become the most least basic. And here in the case of pyridine, these electrons are easily available, and the Bronsted, right? This can easily accept that hydrogen proton and it can form a stable pyridinium hydrochloride. So here also it is very easier, like it is a secondary amine. It can easily take that proton and form a stable, one of the more stable piperidine hydrochloride salt. Okay, this is about Bronsted theory. Okay, these are good Bronsted as bases. This is not a good Bronsted base. It is also not good Lewis base because these pair of electrons are not available at all. According to Bronsted theory, Lewis theory, the Lewis base has to donate pair of electrons. These electrons are not at all available, hence it become a very least basic. Here, yes, these electrons are available, these electrons are also available, but the nitrogen in the pyridine is sp2 hybridized, but the nitrogen in the piperidine is sp3 hybridized. We have one for rule, that is the any element that is especially electronegative element in sp2 hybridized is more electronegative than sp3. So nitrogen is more electronegative in the case of pyridine, that is less in the case of piperidine. So electronegativity means they have to accept electrons, not to donate electrons. So it, as the electronegativity value of nitrogen in pyridine is more, which is not easier to donate this pair of electrons. But here the electronegative value of nitrogen in piperidine is less, which is easier to donate that lone pair of electrons. So this is about the electron theory and also the Bronsted. These two theories, which one? Bronsted and also Lewis. So this is not a good Bronsted base and also not good Lewis base. This is a good Bronsted base but not a good Lewis base. This is a very good Bronsted base and also very good Lewis base. Hence this become the most basic. This is piperidine, and pyrrole become a least basic, and the pyridine have the moderate value of basic strength. And it is also confirmed by their pKb value, as already you've seen. So among these three concepts, one is Bronsted, another one is Lewis, and also confirmation by their pKb values, we can determine the basic strength, and we can easily compare the basic strength among these three compounds. Yes, this is about the basic strength of these compounds. And thank you. This is the last topic in this chapter. I have been selected, the heterocyclic compounds. Please do watch all the videos and please like all the videos and watch them completely. Then you'll get the whole chapter and the idea of the whole chapter. And please like my videos and keep in touch. Keep watching. So we will get also updates of the new chapter that I am going to uploading from the next days. Thank you. Thank you for all your support.